Hi, Chem 101 students. Welcome back for week 2. Week 2 is going to be all about measurements. So we'll start with the basics in this lecture, and then we'll have 2 more to talk about conversions and also temperature and density. So in this lecture, we're going to cover scientific notation, the metric system. We're going to cover units and types of measurements, in particular metric units. We'll talk about the ideas of accuracy and precision, and we will get to significant figures, which are a way of writing down your measurements so that they represent the accuracy of your measurement. So let's start with scientific notation. In chemistry, we're going to be dealing with very large and very small numbers all the time. We talked a little bit about atoms and said these are really, really small things. So if we're talking about any significant amount of stuff, we're talking about a whole bunch of atoms. And if we're talking about how big the atoms are, we're talking about really, really small numbers. So scientific notation is going to be really important in chemistry. So scientific notation is used for very big and very small numbers. An example of a very small number is the radius of a carbon atom, and that is 9.1 times 10 to the minus 11 meters. A meter is, about 3 feet. So it's really, really small, basically. What does that mean? 9.1 times 10 to the minus 11. That's a number written in scientific notation. So what this means is that the number, the radius of the atom in meters is 0.0000000000091 meters. Now, it's not very convenient, though, to write all of these zeros. So what we do instead is we write this value, 9.1 times 10 to the minus 11. That is equivalent to what we have here, down here, with all of the zeros. If we were to move this decimal place 11 places to the right, it will be right next to the 9, like we see here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And so this 10 to the minus 11 is indicating to us that the number is actually smaller, such that the decimal place is actually 11 places to the left of where it's written here on the 9. So that's an example of a really small number and how it's much easier to write it in scientific notation than in standard notation. Also, we'll be dealing with really big numbers, like the number of oxygen atoms in 1 milliliter of water is 3.3 times 10 to the 22nd. So when you write this as a regular number, it's 3 and then with 21 zeros behind it. So this is a hugely, enormously large number, and we don't want to be writing all of these zeros. So that's why we write in scientific notation. It really helps in this regard. And if you were to count how many spaces, you would have to move this decimal point, which is here, in order to get it right over here. That movement would be 22 spaces. And so that's how we write scientific notation. Let me give you a couple more examples. So here, as we saw, the big number had a positive exponent. So that's how you can recognize a number that is big. So let's say you see written 4.5 times 10 to the 9, and you want to make it this number here. Well, you would do that by taking a decimal and moving it in a way that would make the number big, because 10 to the 9th is a positive exponent, and that is indicating a big number. Okay. And so, yeah, this 10 to the 9th is a positive exponent. So if we wanted to change this scientific notation to standard notation, we would move the decimal point 9 places in a way that makes the number bigger. 1, 2, 3, 4, 5, 6, 7, 8, 9, right? And if we're going the other way, and we want to move if we want to create the scientific notation, well, we start with where the decimal point is here. I'll go to the next slide. And we would move it 9 spaces to the left to make the scientific notation. So we'd say 1, 2, 3, 4, 5, 6, 7, 8, 9. And that puts it just to the right of the first non-zero digit. And that's where the decimal point goes when you write it in scientific notation. Okay, so take-home message here. Big numbers have positive exponents on the 10. And the 10 is indicating here the difference in the position of the decimal point. Numbers with positive exponents are big. Numbers with negative exponents, so you can see up here the negative exponent, they are small. So this fact that this scientific notation here has a negative in the exponent, this indicates that you are talking about a very small number. If you wanted to take this and make it into the number that we see right here, well, we would have to move the decimal point in a direction that makes the number smaller. So if we're taking this scientific notation and writing it as the standard notation, we would move the decimal point in the direction that makes the number smaller. That would be 1, 2, 3, 4, 5, 6, 7, 8, 9. And so the decimal point would end up going right here. And we'd put zeros in all the empty spaces. 0, 0, 0, 0, 0, 0, 0, and 0. So that would be this number. That's how we get this number. Now, if you have the standard notation number, like we've got right here, so this is our standard notation number, and we want to make it into a scientific notation number, well, first we know that the decimal point is going to have to go to the right of the first non-zero digit, which is the 4. So we would write the decimal point such that it's just to the right of the first non-zero digit. And then we would count the number of spaces that it would need to move. You need to move the decimal point to get there. We'd say 4.5 times 10 to the, and this would be a minus because we see that this number is small. It's smaller than 1. And we've moved the decimal point however many spaces it takes to get to the right of the 4. So 1, 2, I actually have it on the next slide. So we'd have to move it 1, 2, 3, 4, 5, 6, 7, 8, 9 to get it just to the right of the first non-zero digit. So we'd write the scientific notation as 4.5 times 10 to the minus 9 because this number is small. This number here, it's smaller than 1. And so that's how you do scientific notation. Again, if you have a big number, it will have a number bigger than 1. It will have a positive exponent in the scientific notation. If you have a small number, it will have a negative exponent in the scientific notation. Now, very regularly, you're going to have to put scientific notation into your calculator, and this is why it's so very important that you have a scientific calculator. And these scientific calculators are going to come in 2 different basic types. They're going to be here a dual line type like this Casio, which is quite similar also to the TI that I've shown you. So you may have a Texas Instruments or a Casio. What you want is a good scientific calculator that has some EXP. It also has log, so you see log here. Now I brought up the Casio because it doesn't have one that says EE or EXP. Its one actually says times 10 to the x. If you have one like this, it should work like you expect. Just you can check it in this way. Do like 3,000, 3 times, whoops, don't press times like this. Don't do what I just did. So I made a mistake. Press 3 and then use your EE or EXP or this button if you have a Casio. And that does times 10 to the power of. Then you just press 3 and that equals 3,000. Okay. And you divide by the same thing. 3, press your EE or EXP or this one if you have a calculator. 3. And it equals, and you should get 1. If you don't get 1, that means your calculator's EE or EXP isn't very good. Notice if I don't use my EE or EXP, what happens? I do 3 times 10 Some people want to do this sometimes. To the, and then they'll go to the power of 3, and then they'll say divide by 3 times the 10, and then they say the power of 3. Don't do this, okay? Because look, it's not going to give you 1. This should give you 1. It doesn't. It gives you a million. Because if you don't use your EE or EXP, it thinks that you want to multiply by this times 10 to the 3 instead of divide by it. So don't ever do this. See how this is wrong? Don't do that. Instead, use your EE or EXP. It will look like, it might look like this. So this is what it looks like on a single line calculator. You may have a single line calculator. You can tell the difference because when you type into the double line calculator, it shows you what you're typing in, and if you press divide or plus or something, it will continue to show you what you have on the screen until you press equals. It will show everything you type. Whereas if you have a single line calculator, I'd do like 3EE3, and that's what it looks like on this one. It looks different on every calculator. This means 3 times 10 to the 3. But if I press divide, it turns it into standard notation. That's very common on a single line calculator. But I can still do 3EE3, press equals, and I'll get 1. So make sure that you are using your EE or EXP button, okay? And you saw a couple examples of what it will look like. It will look different on every calculator. Also, if you want to put a negative exponent, make sure to use the plus or minus key or the parentheses minus key, not the subtraction key, because that's a completely different thing. So let's say, and your calculator may look different depending on which one it is, but these all mean 6.3 times 10 to the 8. Let's say I want to put a negative exponent. I'll show you guys an example of a negative exponent. If I put, if I want to put, let's say, 3 times 10 to the minus 3. So I do 3 times 10, and then I don't use the subtract here. I use minus 3. And that will give me, well, this one likes to do fractions. If you have this calculator, you can get it to show you the decimal by pressing this button here, the SD. And there it will show 3 times 10 to the minus 3. And if you need help with your calculator, make sure to come to office hours so I can help you with that. Here, if we put 3 EE, we go, this one has the plus minus 3, and that will give us, whoops, I did something wrong here, 3 EE or EXP minus 3. Notice I didn't use the subtract, I used the plus minus. This is giving me the wrong thing. 3 EE. So there we go. Okay. So it's kept wanting to divide by something. All right. And so that's how you input scientific notation into your calculator. And you'll definitely want to be doing that when you're doing the homework. So a lot of the homework is going to be practicing inputting scientific notation into your calculator this week. So that's the lesson here on scientific notation. Now we're going to start to talk about why we're writing all these numbers. And we're writing all these numbers so that we can make measurements, or quantitative observations, also called measurements. And so we're going to be making measurements in the metric system, not in the imperial or American system. That's what scientists do. We use the metric system for reasons I think you will understand very quickly. It's a lot easier than the imperial American system. So for length, we're not going to use feet or yards usually. We're going to use meters mostly. We'll use a little feet and yards right now while we're doing conversions, but later when we're doing real science, we don't use those. We use meters for length. We use liters for volume, not gallons or quarts. And we'll use grams for mass, or kilograms. We'll have prefixes for these as well that adjust their size. but these are going to be the units that we are using the most in chemistry: meters, liters, and grams. So let's talk a little bit about each of these units. So how does a meter compare to something you know? A meter is about 1.09 yards, or a little bit longer than 3 feet. A centimeter is what's used for measuring things that are smaller than a meter. And the way a centimeter works is 100 centimeters equals 1 meter. And I'll be explaining this in a little more detail in a minute. A millimeter is even smaller than a centimeter. A millimeter, there's 1,000 millimeters in 1 meter. Or equivalently, that means there's 10 millimeters in 1 centimeter. How do we get that relationship? Let me show you. So we already said that 1 meter is the same as 1,000 millimeters. So millimeters are very small, 1,000 of them fit in a meter. And that is also equal to 100 centimeters. So if we want to know the relationship between a centimeter and a millimeter, we could divide both of these by 100. If I divide 100 by 100 here, that's going to equal to 1. So I can say that that cancels, or it equals 1. So 1 centimeter. And then if I divide here by 100, 1,000 divided, whoops. I don't want that 0, I want 100. So 1,000 divided by 100 is 10. And we still have the units millimeters. So something I want to point out to you here too is that what's going to happen a lot is that we're going to treat our units like x's and y's. They're going to be treated like variables in your algebra class. So for example, on the side here, let's say that we had this situation. We had 4x equals 2y, and you're in your algebra class. Well, your millimeters and your centimeters are like, your x's and your y's, okay? So if I divide both sides by 2 here, I get 2 divided by 2, which is 1. We would say that those cancel. Anytime something divides to 1, we say that it cancels. We'd have 1y, or just y. And here we'd have 4 divided by 2, which is 2, but we would still have the x, okay? And so notice how we use the variables just like the units, just like we would variables in algebra. They're going to work exactly the same way. We're going to do a lot of this canceling, where we divide one thing by itself and it becomes 1. And so we just say that it cancels because any number times itself times 1 is just the same as itself. So we could also call this, whoops, I'm going behind myself here. Oh crap, I should have been looking there. So whoops, let me just write it above. So it would be 2x equals 1y, or equivalently 2x equals y. I should have been paying attention to where my head was. So the point is that we treat these units like variables in algebra, and we keep them along like an x or a y. So how am I going to memorize these? Because you will have to memorize them. So to memorize them, think of centimeter. We said earlier that 100 centimeters are in 1 meter. So a way to remember that 100 is like a centipede, which supposedly has 100 legs. It usually has less. Or century, you think of 100 years. That's one way that you could memorize that there are 100 little centimeters in 1 meter. What about milli? So we said earlier that 1,000 millimeters fit in 1 meter. Okay, well, then how are we going to remember what milli means? Well, if you think of a millennium, it's actually spelled millennium, but you can think of milli in that way and remember that it's 1,000 little millimeters in 1 meter. Remember, centimeters and millimeters, these are going to be smaller than the regular meter. So a lot of them are going to fit in a meter. oops, I wrote on this. How many legs does a millipede have? About 1,000. Okay. So what about for longer things, longer than a meter, bigger than a meter? We would use a kilometer or kilometer, as they're called. This is for long distances. 1 mile is about 1.609 kilometers. So a mile is significantly longer than a kilometer, but it's about 1.6 kilometers. So the prefix kilo means 1,000. So this is the way these prefixes work. I told you I was going to tell you this in a little bit more detail. When I say kilometer, so kilo meter, this kilo, what kilo means is the number 1,000. So when I say kilometer, I just replace the kilo with 1,000 because that's what it means. Kilometer means 1,000 meters. Okay, and there's a similar thing that goes for centi and milli that I'll show you in a moment. So kilometer means 1,000 meters because kilo means 1,000. That's what it means. So milli actually means 1/1,000th. So milli is 1,000 times smaller. Kilo is 1,000 times bigger. And notice how convenient this is compared to like feet and yards. Okay, we're talking about millimeters, centimeters, kilometers. They're all related to each other by like 100 or 1,000. This is really, really easy to deal with. It's always easy to multiply or divide by 1,000 or 100 because we just can move the decimal essentially. But if you're talking about lengths in the imperial American system, you're talking about, okay, how many feet is in a yard? 3 feet in a yard. Okay, how many feet are in a mile? Like 5,000 something. I can't even remember. It doesn't really matter because we're not going to use miles and feet and yards. We're going to use meters and kilometers and millimeters and centimeters. They're much easier. You don't have to memorize something totally random, some totally random number. It's always a multiple of 100, a multiple of 10, 100, 1,000, something like that. So that's for distance. Distance is all about meter. Now for volume, the base unit, so just like the base unit for length was meter, the base unit for volume is liter. And what volume means is the amount of space that something takes up. So a liter is approximately equal to a quart. Again, how many quarts are in a gallon? Do you remember? I think there's 4. How many pints are in a quart? How many pints are in a gallon? It's all very confusing. Instead, we're going to use liter, which is indicated by a big L. For small volumes, just like when we did small distances, we used millimeter. If we're going to do small volumes, we use milliliter. And we indicate it with the little m right in front, milliliter. And 1,000 little milliliters fit in a liter, just like 1,000. Remember, 1,000 millimeters are 1 meter? Well, 1,000 milliliters are 1 liter. Works exactly the same. Now, one prefix you may encounter that we won't use a lot in this class, but if you're going to be a nurse, you might see it a lot, is the deciliter. Because it's often used as a measurement for an amount of blood. And so a deci is 1/10. So 10 little deciliters fit in 1 liter. And so you might count a number of deciliters or measure a number of deciliters of blood. That's a very common measurement unit for blood. Now, there is one extra thing. This is especially important for you guys going into the medical field. If you hear like on the medical shows some doctors talking, it's like get me 10 cc's of something stat, and they say cc's a lot in the medical industry instead of milliliters, but they mean the same thing. They mean a cubic centimeter. So a milliliter and a cubic centimeter are the same thing. This is something you should have memorized. 1 milliliter is the same as a cubic centimeter or a cc. This is very important. So I gave it its own slide. If you want to calculate volume, you know, you can measure it by measuring, you know, how much in a measuring cup or something. But you can also calculate a volume by measuring the dimensions of something, like a box here. So the volume of a box, you may remember from earlier math classes, is the length times the width times the height. And so, for example, if we had a box that had a length of 2 centimeters on one side, 1 centimeter on another, and 2.5 centimeters on another, to get its volume, we multiply these together. And what I really want to point out here is what happens with the units. So let's compare this to algebra again. Let's say you had 2x times 3x times 1x in your algebra class. So this would be the same as 2 times 3 times 1, and then times x times x times x in your algebra class. So you'd have 2 times 3, which is 6, times 1, which is 6. So you'd have 6, and then for your x, you'd have x times x times x, which is x cubed. The same thing happens for units. Again, treat your units like an x or a y. So for our numbers, we have 2 times 1, which is 2, times 2.5, which is 5. And we have centimeters times centimeters times centimeters. That is centimeters cubed, or cubic centimeters. Remember to treat your units just like x's and y's. If you're multiplying units together, make sure that you're multiplying them together like you would an x or a y. Finally, we get to mass or weight. So gram is the way we measure mass. A gram is a very light type of thing. So there are 454 grams in 1 pound. So you can imagine that a gram is way less than a pound. It's a pretty small weight. We usually call weight mass in science too, because weight is referring to the effect of gravity on a mass, and mass is a measurement of the actual amount of stuff. Practically speaking, they're the same as long as you're at the same place on Earth. Just like with the previous units, if you have larger masses or larger distances or larger anything, you can use kilo. Remember that kilo means 1,000. So kilogram means 1,000 gram. Kilo and 1,000 mean the same thing. And a milligram is the smallest weight that we can usually measure easily. A milligram is a very small amount. And so just like 1,000 millimeters fit in 1 meter, 1,000 milligrams fit in 1 gram. So finally, we're going to summarize our metric prefixes here. Now the ones that we have focused on were right in here. We focused on milli up to kilo. And that's all I want you to memorize. There are bigger ones like mega, which means 1,000,000. And there's giga, higher than that right here. So there's mega. There's giga right here. That means 1 billion. And then there's micro, that's very small, 1 millionth. There's nano, 1 billionth. Pico, 1 trillionth. Very small. But the only ones I'm going to have you memorize for this class are kilo, deci, centi, and milli. Those are the only ones that I'm going to use. Now you may see the other ones show up in homework, but you'll have this chart that you can refer to if you need to. And just to summarize how this works, so you're going to memorize kilo, deci, centi, milli. With kilo, as I said, kilometer means 1,000 meters, because kilo, what kilo means is 1,000. Kilo means 1,000. Okay. So kilo here means 1,000. Example 2 here, milli. What does milli mean? Well, milliliter, milli means 1/1000th. So milliliter means 1/1000th of a liter, because milli means 1/1000th. What's in orange here means the same thing. So you can just simply memorize that 1,000 little milliliters fit in a liter. But if you wanted to relate it to your chart here, I'd say using fractions isn't usually as convenient. So what people usually want to do is multiply both sides of this by 1,000. So if you multiply 1,000 on this side, we're basically multiplying 1,000 over here 1,000 times, and then we're multiplying times 1,000 over here. We get this. So 1,000 milliliters is 1/1000th times a liter times 1,000. We multiplied both sides by 1,000. Well, that leaves us with 1,000 milliliters on the left, and then we have 1,000 here divided by 1,000. Well, that equals 1, right? So this equals 1. And so then on our next line here, we'll have 1,000 milliliters equals 1 liter, because all of this here equals 1. 1,000 divided by 1,000. So I'd say it's probably easier to just memorize that 1,000 milliliters fit in 1 liter, or 1,000 millimeters fit in 1 meter. But you can do this math too if you have the chart, and that will get you the same result. So this is the same result as what we memorized earlier. So now let's talk about how we're going to write down our numbers. So this is turning into a long lecture. I guess this is going to be more like 40-45 minutes. This will be the longest of the 3 lectures. The other 2 will be shorter. But this will be a good place to start. So now we want to talk about how accurate our measurements are. So we're going to be making, or at least virtually making, all kinds of measurements. But we want to know, are our measurements any good? And in science, accuracy has a very specific meaning. It means how close a measurement is to the real value. Now that's kind of tricky in science because we don't usually know what the real value is, otherwise we wouldn't be measuring it. But we hope that when we make a measurement, and if we use a good tool, we will have an accurate measurement that's close to the real value, that's useful for us. So measured values, that their accuracy is always going to be limited by what tool you use. The better tool you use, the more accurate you can be. If you use your arm to measure something, like if I measure the length of this monitor in front of me with my arm, that's probably not going to be very accurate. But if I take out a tape measure, which is a better tool, I can probably get a more accurate measurement. There are certain things that count as true values. In terms of measurements, there's only one type of measurement that's exact, and that is counting things. So if you count things one by one, and there can't be a partial one, like how many pennies, like if you say, 320 pennies, this is exactly 320 because you can't have a half a penny. It wouldn't be a penny anymore. Or you say, 52 words on your essay. These were measured by counting them. And so these have infinite accuracy because you can't have a partial. You have 52 words. You don't have 53, you don't have 51, you have exactly 52. And there's going to be one other situation where we have exact numbers. And it's important to recognize that these have perfect accuracy, unlike other measurements. Finally, in science, we also have the term precision. Now, precision and accuracy in regular language often mean the same thing, but in science, they don't. What precision means in science is that when you take multiple measurements, which we often do in science to make sure that we didn't make a mistake and to get closer and closer to a better answer, if we make a measurement multiple times, our precision indicates how close those measurements are to one another. If they're very precise, then we feel more confident that we're more accurate because our measurements are coming out about the same every time. If our measurements end up being imprecise, they're all spread out and not the same, then we may question how we're making our measurements and try to make them better. Scientists, always try to measure a value multiple times to make sure that they're more likely that they're right. Of course, they can't be certain that they're correct because you wouldn't be making the measurement in the first place if you already knew what it was. But we hope that if our measurements are more precise, then they will also be more accurate. Finally, When we write down numbers, we want to have an easy way of indicating how accurate our results actually are. So significant figures is a way to communicate how accurate we think our measurements are. So these are the rules for how you will count in a number that's written, what digits are meant to be significant, which ones are part of the measurement, and which ones are not. They're simply placeholder zeros, essentially. So any non-zero digit is going to be a part of the measurement. It will be significant. So any non-zero digit will always be significant. It's only the zeros that may or may not be significant. Zeros at the front of a number will never ever be significant figures. They're just there to make the number small. They're just a placeholder to make the number smaller. So for example, here we have 0.0028. This has two significant figures, the 2 and the 8. These are front zeros. They're only there to make the number small. They're not a part of the measurement. So front zeros like this are never counted as significant figures. So our measurement here is said to have two significant figures, the 2 and the 8. Zeros in the middle of non-zero digits are definitely a part of the measurement. So they're always significant figures. So here, this measurement has two zeros, one between the 3 and the 8, and one between this 8 and this 8. So those zeros are significant along with the other non-zero digits. So all 5 of these digits are significant. Finally, zeros at the end of a number are significant if there is a decimal point written. And an example here is 0.004080. So these are front zeros. They are not significant. This is a middle zero between two non-zero digits. So it is always significant. So front zeros, never significant, not significant. Middle zeros, always significant. This is a middle zero. The end zeros are significant if there is a decimal point written. And there is a decimal point in this number. So the reason why this 0 is significant is because we could have written this number as, instead, we could have written this number as, we could have written it as 0.00408 without the 0 at the end. Okay, and we could have done that. But we didn't, because we were trying to say something with this 0. We're trying to say we actually know that this is a 0 and not a 1 or a 2 or a 9 or anything else. It's a 0. So these zeros, they're not significant because they have to be there. If they aren't there, the number will be too big and it won't be right. But this 0 did not have to be there. The number would have the same value without it. We wrote it because we wanted to indicate that this is a 0 and not something else. It is a significant figure. So those are how you recognize what are significant figures. I'll run you through a few more examples here. So in this one, we have 4 significant figures. Front zeros, never significant. This is a number less than 1. It has a decimal point. So front 0 is not significant. Middle 0 is significant. So this is the first sig fig. 0 is the second. This 2 is the third. And the 0 at the end is significant because there's a decimal point. So 4 sig figs, the 5, the 0, the 2, and the 0. Now here's an example with n zeros that do not have a decimal point. There's no decimal point here. So what we're saying is we don't really know what these numbers are, so they're not significant. Numbers greater than 1 when no decimal point is written. Zeros at the end, these n zeros are not significant because there's no decimal point. So our only sig figs are the 1, the 2, and the 3. These n zeros are not significant because there's no decimal point. This is a middle 0, so it's always significant. 3 sig figs, the 1, the 0, and the 6. This number, 10.0. This has n zeros, and there is a decimal point. It's a number greater than 1, has a decimal point. These n zeros are significant. So all 3 are significant, the 1 and the 2 n zeros, because there's a decimal point. This is a number greater than 1. It but it has an end zero and no decimal point. So this zero is not significant. This is a middle zero, so it is significant. So the sig figs are 4, 0, 2, and 1, and this zero is not significant. 4 sig figs. Here we have a number smaller than 1 with front zeros. Front zeros are never significant, so it's only the 3 and the 2 that are significant. 2 sig figs. And now one note about scientific notation. So there's something really great about scientific notation, and it's this. Scientific notation is never written with a front zero because we always put the decimal to the right of the first non-zero digit. Also, if it has middle zeros, those are significant anyways because they're always significant. And end zeros will always be significant because there's always a decimal point in a scientific notation number. So every number that's written before the times 10 to the power is significant. And if a number is significant, you do have to write it here as well. So all 4 of these are significant because we have end zeros, but there's a decimal point. In scientific notation, because of the way it's made, all numbers that are in front of the times 10 to the power will always be significant. We ignore this part. All the sig figs are wrapped up in here. So when we're making a measurement, how do we know how many sig figs that we should write down when we're making the measurement? Well, these sig figs here, or these instruments here, they operate in a different way. Here we have a ruler down here with little tick marks. Here we have a balance with a digital display. If your instrument has a digital display, every number that shows is a significant digit, so you should always write it. 3.080 kilograms. Write them all. They're all significant, so write them all down. If you're reading an analog instrument, you need to read between the lines. That's what I call it, reading between the lines. So here we can see that if we look at this ruler, every single tick mark represents 0.1, and these are centimeters, by the way, so it doesn't say, but these are centimeters. So this one here is 0.1 centimeters. This right here is 0.2, and this one here is 0.3, and so forth. So right here we have 1, 1.2, this is 1, this one's 1.2, this is 1.0, 1.1, 1.2, this one's 1.3. So this one is 1.3, and this one right here is 1.4. So we know that our end of our slab here is between 1.3 and 1.4. It's right there. So what we do is in our mind, we divide this little region right here between 1.3 and 1.4. We divide it into 10 little pieces in our mind, into tenths. And depending how far it is, we write a number. If it were halfway between, we'll write 5, because it's 5/10 halfway between. Here I'd say it's about 7 or 8/10, so I'd write 1.3 because this measurement is greater than 1.3 and less than 1.4. And then I'd write 6 or 7 or 8 here. You could put also 6 or 8 would be okay, because we're kind of eyeballing that last one. So the last sig fig has a little bit of wiggle room to it, okay? But you do need to write that last sig fig. So since all of our lines went to the 10th, since we had a line for 1.3, we're not going to stop at 1.3. We're going to go one more digit and say how far past 1.3, how close to 1.4, 7/10 of the way. That's how we read that. We'll also do similar readings for volumes. So volumes are usually measured in graduated cylinders or other glassware in the lab. And when you put the water in there, they make a little bubble, as you can see here in these pictures. So you can see here a little bubble downward like this, like that. And so we call this a meniscus. And when you read these, you're going to read from the bottom of the meniscus. So right here, we're going to be looking at the bottom of the meniscus. And if we look on this left example, these are going to be milliliters. Okay, let's say this one's 35. So this line here is 36, and this one is 37. So we know that our volume is greater than 36 and less than 37. And if I look at the bottom of the meniscus, it looks like it's about halfway between 36 and 37. So if I'm dividing this into 10 little pieces, it's half the way. So 5 of those little pieces up. So I see that it's greater than 36 and less than 37. So I write 36, and then I write 0.5 because right here I can see that it's halfway between 36 and 37, or 5/10 of the way. So I write 36.5. Now what if it lands right on the line, like this here? The bottom of this one is right on the line. So these are also milliliters right here. This is 40, this one's 41. And from what I can tell, it's right on the line 40. But I'm not just going to write 40, because I know that I'm more accurate than that. I need to say that it's right on the line 40. And the way I do that is by saying 0. So I could put a 0 here. If I think it's right above the line, maybe I would put a 40.1, meaning, 1/10 of the way from here up to here, right? But it looks to me like it's right on the line right here. So I'm going to say 40.0. And that's how you read this instrumentation properly for the correct number of sig figs. Finally, after we make these measurements, we might want to do some math with them. This is going to happen a lot. Okay, so if we're going to do some math with them, then we're going to want to have some rules about how many sig figs we write in our result. So when we're doing calculations using significant figures, we're going to have rules that make it so that our answer cannot be more accurate than our least accurate data. Okay, the answers cannot be more accurate than our least accurate data. And we're going to have 2 different ways we do this. One for multiplying and dividing, and one for adding and subtracting. So if we're multiplying and dividing, here's an example where we're dividing. Okay, so the rules are, when we're multiplying and dividing, our answer will be rounded so that it has the same number of sig figs as the data with the least number of sig figs, because your data with the least number of sig figs is the least accurate data. So you don't want to be quoting a result that's more accurate than your worst data, because then you're lying about your accuracy. So here we've got 2 numbers we're dividing. We're dividing 2,550 divided by 88,000. And so here our sig figs go up to the 5. So it's the 2, the 5, and the 5 that are significant. So this number has 3 sig figs. Here, and n zeros are not significant because there's not a decimal point. Same thing with 88,000. It's got 3 n zeros. Those are not significant because there's no decimal point. So it's the 8 and the 8 that are significant. We have 2 sig figs here. And so when we punch this into our calculator, you will get 0.0289772. That's what your calculator would tell you. Remember, your calculator does not know what the heck significant figures are. It's just going to spit out a number at you. It's your job to get the right number of sig figs. So when we write this, these front zeros here, the 0 and the 0, these are not significant. The 2 is the first sig fig, because front zeros are never significant. So your first sig fig is the 2, and your second sig fig is the 8. And that's where you want to round, right here. So what you do when you round is you look at the next number. If it's 5 or greater, you round up. If it's 4 or less, you leave this number alone. So this 8 is going to get rounded up to a 9, since we have a 9 here, which is greater than 5. So we state our answer as 0.029, where we rounded the 8 up to a 9 because there was a number larger than 5 next to it. 5 or larger, you round up. Now, if you're adding and subtracting, you want to do things very, very differently. What matters when you're adding and subtracting is the place value of the numbers, not how many significant figures there are, but what is the place value of the last significant figure. So what we want to do is we want to line our numbers up like we're in grade school. So you see it right here. We line our numbers up. We line the decimal points up. If we're adding 25.902 to 6.8034, we line them up. And then we punch them into our calculator. And when we punch them into our calculator, it tells us 32.7054. Okay. Well, the way we're going to decide where to round is we look where the last sig fig is. The last sig fig here is the 2 on this one and the 4 on this one. So we're going to want to round at the place value of the number that has the fewest place values. So here, it's more to the left. We're rounding right here where the 2 is, not where the 4 is. So my last sig fig is going to be right here, 3 after the decimal, the same spot where the 2 is. That's my last sig fig. Since this is a 4, I round this down, which means I leave the 5 as is, and I get 32.705. So remember to use those different rules when you're doing addition steps versus multiplication and division steps. If you have more than one type of step in your problem, you're going to need to use the rules for each step when you do each step. What about scientific notation? Well, remember, I told you that when numbers are written in scientific notation, all the digits that come before the number 10 to the n are significant. Okay. So most of the time when we write a number in scientific notation, it's merely for convenience. For example, 3,000 kilometers. However, if we wanted to write 3,000 kilometers with 2 sig figs, there would be no way to actually write it with 2 sig figs, because this 0 does not look like it's significant because there's no decimal point. However, if we put a decimal point, if we wrote it instead like this, 3,000, and we put a decimal point here, well, this is written with 1 sig fig, we have right here, because the n zeros are not significant. This is written with 4 sig figs. Neither of these are 2 sig figs. So what we can do instead is write this as 3.0 times 10 to the 3 power. And here now we have 2 sig figs, the 3 and the 0. Also, if you are going to write a number in scientific notation, make sure you write it with the correct number of sig figs. So for example, if we're converting 0.0410 liters to scientific notation, well, here the front zeros are not significant, but the end zero is significant because there's a decimal point. So the 4, the 1, and the 0 are significant. So if we're writing scientific notation, this is a number that's smaller than 1, so it will have a negative exponent, and that exponent will be 1, 2, the number of spaces it takes to put it just to the right of 4. Then we make sure that we write the 0, because the 0 is significant. If the 0 weren't significant, we wouldn't write it. But this 0 is significant, so we do write it. Finally, if we're multiplying and dividing in scientific notation, we'll probably need to put this in our calculator. So you're going to want to use the EE or the EXP button here. Okay. But if you're subtracting and if you're adding, you're going to have to be careful about the way you do this. So let me show you a couple of examples. So let's say we are asked to divide 3.2 times 10 to the 5th, and we're going to divide that by 4.86 times 10 to the 2nd power. So we're probably going to want to put this in our calculator. But before we do, we should think about how many sig figs we have. We have 2 sig figs here, the 3 and the 2. We have 3 sig figs here, so 3 sig figs, the 4, the 8, and the 6. Now let's go ahead and punch them in your calculator. Make sure when you punch them in your calculator, you use the EE or the EXP button. Okay, so we would put 3.2, and this is on our Casio, this is the EE or EXP button, times 10 to the 5. Don't ever hit times and then 10 and to the power. That's not what you want to do. And we'll put divide by 4.86. Then don't hit times, hit the EE or the EX button or this button here, times 10 to the 2nd. And our calculator again spits out a bunch of numbers at us. We can write some of them down here. 6, 5, 8.4343, and so forth. I don't really need the rest because I need to round so that my number has only 2 sig figs. So my sig figs will be the 6 and the 5. I'm going to stop where the 5 is. Because there's an 8 next to it, I'll round up to the nearest higher 10. It will be 660. Is this 0 significant? No. But it needs to be here or else the number would be too small. 660 is not close to 658. But you should write 660 instead. Now let's do another example. When you're subtracting and adding and subtracting, you probably don't want to just put it into your calculator. So here you'll want to probably convert it to standard notation. Let's say I have 2.7 times 10 to the 2nd plus 3.35 times 10 to the 3rd. What you're going to want to do is instead of just punching this into your calculator, you need to actually convert this to standard notation and then line it up like you're in grade school and add them. So here, this is 270 times 10 to the 2, so this is going to be a bigger number. We'd move the decimal place 2 spaces to the right, 1, 2, and so we'd get 270. And remember, the 7 will be our last sig fig here. Then for this one, it's 3.35 times 10 to the 3rd, so it would be, we'd move it 1, 2, 3 and make it bigger. Again, this is a bigger number than 1. So we would say this is 3350. We put a 0 in here. Okay. 0 in there. And again, the 5 is the last sig fig here. This N0 is not significant. So then we want to add them. 270 plus 3350. So notice how we line them up. And the last sig fig here is 7. For this one, it's 5. Now we can punch it into our calculator. 270 plus 3350. And our calculator gives us 3620. 3620. And the last sig fig is a 2. And we don't have to round. This 0 is not significant. But notice, we ended up with a number that has 3 sig figs, right? Even though 270, or this one, technically had 2 sig figs. This had 2 sig figs. This had 3 sig figs. The number of sig figs doesn't matter when you're adding and subtracting. What matters is the place value. So when you want to add or subtract scientific notation numbers, first convert them into standard notation, then line them up like you're in grade school and add them. And you can use your calculator to do this, just make sure that you get the place value correctly. And so this made a whopping 1-hour lecture video, so this was a full lecture. The subsequent ones will be smaller. I'm shooting for more like half an hour. and I know they will be shorter. This one was quite big. So I hope that that you've gotten some help from this. Make sure to read the sections in your textbook as well if you need a little bit extra practice. These are sections 2.1 to 2.3 in your textbook, was the stuff that I just lectured about. Okay, and I will see you in the next lecture video, lecture 2.1, which will be about textbook chapter 2.4. Okay, see you later. Oops, I can't find it. See you later. Try to stop.